Hi everyone, my name is Hui Minzeng from Northeastern University. Today I'm going to introduce you our new work, Physically Inspired Gaussian Splatting for HDR Novel View Synthesis. The goal of HDR Novel View Synthesis is to reconstruct a 3D scene and render novel views while preserving high dynamic range details, especially in very bright or very dark regions. A very straightforward solution is to use the HDR mode of a camera. For a single image, the camera captures multiple exposures and fuses them into one HDR image. This works well in 2D image capture. However, in 3D reconstruction, we need this process across different views. Storing HDR views for every view is expensive, and more importantly, independently fused HDR images may have inconsistent dynamic ranges across different views. So when we render a video or move the camera, such inconsistency may cause flickering. So in this setting, although HDR views can be available, relying on multi-view HDR supervision is costly and is not always temporally or view consistent. So this actually motivates us to learn the HDR novel view synthesis from multi-exposure LDR observations instead. In this way, most existing methods use LDR images captured under different camera exposures to obtain details of different ranges. However, this setting introduces several challenges. First is the illumination-dependent appearance is not well captured. The same surface may look very different under different illumination levels. For example, the highlights, reflections, and the dark textures can change differently. If the model only treats these observations as simple color variations introduced by changing the color and also the camera exposures, it cannot faithfully recover such kind of 3D appearance. The second is the supervision is mostly implicit. Since HDR ground truth is unavailable, the model is usually trained only with LDR observations. This makes it difficult to directly constrain the reconstructed HDR content. And the third is during experiment, we find that overexposed and underexposed regions received weak gradients during optimization. But these regions are exactly what matters in HDR reconstruction. We will have a deep illustration on this fact later. So to summarize, the key challenge is how to capture the illumination-dependent appearance and how to effectively provide HDR supervision without HDR ground truth, and how to effectively optimize Gaussians in under- and overexposed regions. So now let's imagine a scenario that we are currently in a room. To reconstruct a room with richer dynamic range details, we can think about two different ways of capturing additional information. The first way is to change the camera exposure. This follows the camera ISP pipeline. As shown here, when we increase or decrease the exposure, the whole image mainly undergoes a global intensity change. The bright regions may become saturated, and the dark regions may become more visible. But the change is mostly image level and camera controlled. And the second way is to change the environment illumination. For example, instead of only change the camera setting, we can turn the light on in the room and physically make the scene brighter. In this case, the appearance does not simply change globally. Some regions become much brighter, and some reflections appear or disappear, and the local materials respond differently to the illumination change. So these two operations reveals different response patterns of this kind of HDR signals. Changing camera exposures give us a global, exposure-dependent observation, while changing the ambient illumination give us local lighting-conditioned appearance changes. Such observation motivate us with the PhysHDR-GS, which contains the dual-branch design that we just discussed. To further provide supervision for the HDR content, here we introduce an HDR consistency loss between these two branches. Since explicit HDR ground truth is not available, such consistency serves as a form of self-supervision. It encourages these two branches to agree in a HDR space, so that the model can learn a more reliable HDR representation from complementary observations. In addition, we find that the gradient received by Gaussians are closely related to ambient illumination, which means in very dark or very bright regions, the optimization signals can become very weak, which leads to the gradient starvation. So to address this issue, we further propose an illumination-guided gradient scaling strategy, which adaptively enhances the gradients according to the illumination condition and helps the model to better learn difficult HDR regions. Overall, our PhysHDR-GS combines dual-branch HDR modeling, self-supervised HDR consistency, and illumination-guided optimization to improve HDR scene reconstruction and novel view synthesis. So now let's take a look at the physical radiance composition used in our framework. The idea is to decompose the Gaussian color into two parts: intrinsic reflection and adjustable illumination. Intrinsic reflection represents the material-related appearance of the scene, while illumination controls how much the radiance is received or emitted under different lighting conditions. Based on this decomposition, the two branches model HDR response in different ways. In the image exposure branch, the model applies the camera exposure value T to globally scale the pre-tone-mapped signal. This corresponds to the change of the camera setting, and the scene itself is not physically changed, but the captured image becomes globally brighter or darker. In the Gaussian illumination branch, instead of changing the camera exposure, the model directly modulates the illumination term of each Gaussian. This allows the radiance intensity to be rescaled locally. Different regions can respond differently to illumination changes, which better captures lighting conditioned appearance variations, such as highlights, reflections, and dark regions recovery. So this form connects the method designed with the physical motivation. The camera exposure explains global intensity changes, while the Gaussian illumination explains local HDR appearance changes. Next, we introduce how our framework learns HDR information without relying on HDR ground truth. The first part is the tone-mapped LDR learning. Since the training images are standard camera-captured LDR images, the model first renders the HDR radiance and then maps it back to the LDR space through tone mapping. In this way, the model can be supervised by ordinary LDR observations. Because the input views are captured under different exposures, these LDR images provide complementary dynamic range details. Some views preserve highlights better, and the others reveal dark regions better. However, this kind of supervision is still indirect. The loss is applied after tone mapping, so the HDR radiance itself is not explicitly constrained. To address this issue, our paper further introduces a self-consistent HDR learning. The key idea is to use these two branches to supervise each other in HDR space. The image exposure branch and the Gaussian illumination branch produce HDR predictions from different response mechanisms. By enforcing a cross-branch HDR consistency loss here, the model obtains a more direct constraint on the HDR representation. So the overall learning process has two levels. The LDR reconstruction ensures that the rendered results match real camera observations, while the HDR consistency encourages these two branches to agree with each other before tone mapping. This makes the HDR learning more stable and more physically meaningful, even when the HDR ground truth is unavailable. Finally, we addressed an optimization problem in HDR reconstruction, the gradient starvation. In a 3D Gaussian splatting, the density and quality of reconstruction depend heavily on whether the Gaussians receive enough gradient during training. However, in HDR scenes, overexposed and underexposed regions often provide very limited learning gradients. Probably you can see here, the tall map curve is kind of squeezing the dynamic range and cut off extreme valleys, so that saturated pixels can lose highlight details and extremely dark pixels can lose texture information. As a result, the Gaussians in these regions may be not sufficiently updated or densified. We observed that this problem is related to the illumination deviation. When the illumination of a Gaussian deviates more from the normal range, the gradient it receives tends to be smaller. In other words, the regions with stronger illumination deviation are more likely to suffer from weaker gradients. Based on this observation, we proposed the illumination-guided gradient scaling strategy. The idea is to adaptively rescale the gradient of each Gaussian according to its illumination deviation. If a Gaussian lies in a different or very difficult illumination condition, its gradient is amplified, so it has a better chance to be updated or densified. This strategy helps to recover details in challenging HDR regions, especially in highlights or shadows, where the standard optimization may fail due to insufficient gradients. In an experiment, we conduct comparisons on both realistic and synthetic dataset. Both scenarios shows that our competitive perceptual performance and our superiority over SOTA methods on most metrics. This highlights the benefit of jointly modeling image exposure and ambient illumination for HDR novel view synthesis, which enables both faithful LDR reconstruction and perceptually pleasing dynamic range details. For the qualitative results, we provide results on both LDR and HDR results. For each method, we also visualize the residual map with respect to the ground truth to demonstrate the difference. As can be seen, for the LDR scenes, the compared method shows noticeable missing contents for saturated regions, for example, the reflection region here, which indicates unconstrained information loss after tone mapping. But in contrast, our method can effectively preserve fine structures. We attribute this to the cross-branch HDR consistency loss that can provide explicit supervision for regions of high signal intensity. For the HDR scenes, methods such as HDR-NVS and HDR-GS struggles to reproduce the correct illumination level, which results from the absence of the HDR ground truth during training, while our method can actually estimate the lighting conditions by explicitly modeling the exposure and ambient illumination, yielding a very effective reconstruction of details. For example, the edge of the basket. And we provide more qualitative comparisons in the supplementary materials. We conduct a comprehensive efficiency analysis here. Despite the additional radiance composition step, our method remains efficient. We built our method on both vanilla 3D-GS and scaffold, which both achieves real-time inference speed. Compared with the well-performing Gauss HDR, our models delivers faster rendering speed and lower GPU memory consumption, while still offering overall better reconstruction performance. For the ablation studies, we conduct the ablation studies starting from the baseline that contains the image exposure branch only, and then we progressively equip this baseline with the Gaussian illumination branch, the cross-branch HDR consistency loss, and also the illumination-guided gradient scaling strategy to evaluate the contribution of each component. All the ablation studies are conducted under the exposure settings of EXP3, As shown in this table, every component is demonstrated to be effective. For the qualitative results here, it shows that including the Gaussian illumination branch can effectively improve the modeling of the lighting-dependent appearance. For example, the table surface reflection here. And it also shows that the self-consistent HDR learning can help to refine texture distortions. And also, the illumination-guided gradient scaling strategy can effectively help to refine the texture distortions in some shadow regions. So to summarize, in this paper, we propose a physically inspired HDR novel view synthesis framework. To reflect the illumination-dependent appearance, we decompose the Gaussian color into intrinsic reflection and adjustable ambient illumination. An image exposure branch and a Gaussian illumination branch jointly models the complementary dynamic range details. An HDR consistency loss is imposed across these branches to enable self-supervision for HDR contents. The proposed gradient scaling strategy further amplifies the Gaussian gradients to preserve under-densified representation. We conduct extensive results, which all shows our method can effectively reconstruct dynamic range details while keeping the real-time rendering speed. Evaluation studies further verify the effectiveness of each proposed component in our framework. And that's all. Thank you for watching this video.